This is Group H by Western and Eastern Snake River Plain by Emily, Jane, Conrad, Katie, and Megan. We had Section H, which is the extending part of the Snake River Plain through eastern Idaho to western Idaho, shown here on the map.
The Snake River Plain is a large tectonic graben. The Snake River Plain was formed from successive volcanic eruptions of the Yellowstone hotspot as it moved beneath the North American plate from what is now eastern Oregon to its current location in northwest Wyoming. This volcanic activity laid down rhyolite in the Snake River Plain. These rhyolites would later have sediments and basalts deposited. The eastern Snake River Plain is mostly silicic and volcanic basalt with very little sediments. The western Snake River Plain is filled by interbedded volcanic rocks and lakebed sediments. There were two major factors in how the western and eastern Snake River Plain were formed. First, there were multiple volcanic eruptions that laid down layers of basalt. You can see in the top picture that there are many different layers that were laid down by these different volcanic eruptions. The second big factor was when Lake Idaho drained. This caused cutting in canyons due to the flow of water and shaped the land into how it is today. You can see in the second picture how the flow of water over time would cut into the land to shape these rocks. The rocks in this area are around 11 million years old. The rocks are based upon the volcanic activity that laid down different layers of basalt, which you can use the principle of superposition and the principle of cross-cutting relations to determine the age of these rocks.
The Snake River Plain is typically divided into western, eastern, and central sections. The major features of the Snake River Basin is an arced or curved depression across southern Idaho, taking up a quarter of the state. The western portion of this province is in a graben or rift valley that runs for about 30 to 43 miles. A graben is a valley that has very distinct and steep slopes on each side of it. These are caused by a block of land being displaced downwards. Tension and crustal stretching are typically what causes this displacement. This is a result of a normal fault in which the hanging wall moves downward and the footwall is moved upward. This particular basin is filled with volcanic rocks and sediments from lake beds. The eastern part has been warped downward because of the weight of overlying volcanic rocks. There are also caldera complexes starting in the eastern portion of the plain. A caldera is a large depression shaped like a cauldron that forms after a magma reservoir has been emptied. The caldera complexes have originated from Yellowstone, and the presence of more calderas has been assumed. This can be inferred to mean that the source of these calderas is moving through plate tectonic processes. The Island Park caldera is the biggest as well as the most symmetrical caldera on Earth. Also in this region are the Craters of the Moon National Monument, which consists of three major lava fields of preserved flood basalt, as well as sagebrush grasslands. The fields run along the Great Rift of Idaho. Some of these rift cracks are actually the deepest known on Earth. The plain as a whole runs for about 400 miles in length from Wyoming to the border of Idaho and Oregon.
The general geological history of the Snake River Plain province began approximately 16 million years ago. It began to take place on the Oahe Plateau region on eastern Idaho, where Idaho, Oregon, and Nevada borders meet. At first, massive volcanoes were formed, and this has caused the development of the Yellowstone hotspot that we know today. Then, the North American plate moved southwest over the hotspot into Wyoming. This caused the Snake River Plain to form. There are several facts that support this theory. The time transition record of the silica volcanoes is interpreted as a result of this movement of the continental plate. The topographical changes also suggest the validness that this theory has. The land rose due to a thermal uplift of the hotspots, and northeast to the hotspots of the highlands subsided due to the cooling of the underlying crust. This is because of the crustal loading from the erosion of the post-hotspot basis. The location of the continental divide corresponds to the migration of these hotspots as well. The Continental Divide moved eastward across the southern Idaho rivers south of the Snake River Plain and flowed southeast. The substance in wake of the hotspot migration caused a drop in the baseload of the Snake River Plain. This initiated the headward erosion towards the modern side channel that is there today. This led to the stream shifting drainage, and the drainage now went into the Pacific Ocean, as we can see today. The final impact of this landscape came from the Bonneville flood, which swept along the course of the river and had a significant impact in the geological history that this section brings. The current Snake River Plain is a U-shaped depression extending across the southern and central Idaho. The plain runs from east to west, totaling about 400 miles long, ranging in width from the narrowest sections of 25 miles and the largest sections being 50 miles in width. The widest section of the plain is in the most southern central sections of Idaho, or at the bottom section of the U-shape in the plain. The current topography reflects its geological history because the current placement of Yellowstone and the remnants of the volcanic activity in western Idaho. These volcanic activities are shown in places like craters of the moon in the eastern upper section of the Snake River Plain. This suggests the movement of the continental divide moving eastward and explains the rock volcanic activities in western Idaho. The plain continues to reflect the area along the current river flow of the Snake River. Furthermore, the sediments found by the draining of Lake Idaho are present day reflections of the geologic history that happened in this time many years ago.
The main resource in the Snake River Plain is the Snake River Plain Aquifer. The aquifer extends from the western boundary of Yellowstone National Park in eastern Idaho to the Idaho-Oregon border. This resource is used to support the economies of most of southern Idaho. 3 million acres of farmland on the Snake River Plain are irrigated, with approximately 1/3 from wells and the remaining 2/3 from canals. The aquifer can be split into two sections, the eastern and western aquifer. There are two main areas of natural discharge within the eastern aquifer. The springs along the Snake River near American Falls Reservoir have about 2,600 cubic feet per second of discharge, and Thousand Springs, where the collective discharge is about 5,200 cubic feet per second. Humans have a large effect on recharging the aquifer through irrigation water. It balances the water draining into the mountain drainage basins. The western aquifer feeds most of the Treasure Valley with its groundwater. It is made of more coarse sediment than the east aquifer and contains more volcanic rock. Some of the natural hazards in the east-west Snake River Plain are a series of volcanoes. It has been a while since any of the volcanoes have erupted, the last time being the Pleistocene and Holocene periods. The magma flow is minimal, but there is potential to have large pyroclastic clouds from some of these volcanoes. The picture shown on the right illustrates the magmatic and surficial processes that contribute to the evolution of the province. Thank you for watching our video. We learned a lot from this project and hope you did as well. The main resource